This video starts our discussion of measures of central tendency, focusing on the mean. Remember, descriptive statistics describe our data. And when we think about describing our data, probably the first thing that comes to mind is describing what the typical score looks like. We do that with what are called measures of central tendency. In these videos, we'll discuss three measures of central tendency: the mean, the median, and the mode. Probably the most familiar measure of central tendency is the mean or average. The mean is likely the most widely reported measure of central tendency and is equal to the sum of all scores divided by the number of scores, and it's represented by x with a line or bar across the top, or x bar. The mean has a few very helpful and important mathematical properties that we're going to keep coming back to, so let's be certain to note them here. First, the sum of deviations around the mean is equal to 0. In other words, if we subtract the mean from every score and add up the results, you'll always get 0. Mathematically, you can write this as the sum of the quantity x sub I minus x bar is equal to 0. Visually, you can see that here. Let's say you have three scores, 2, 3, and 7. The mean would be 4. If you calculated the difference or deviations between each score and the mean, the sum of these differences would be 0. The total below the mean is balanced out by the total above the mean. A result of this is that the mean is the balancing point of the data. Like a seesaw with scores spread out along the board, the mean is the point where the scores are balanced on both sides. Don't worry, I was assured no elderly Swedes were harmed in the making of this video. Now, just like a seesaw, scores further away from the balancing point or mean have a greater influence. Even a small child sitting out on the edge of a seesaw can balance an adult sitting near the balancing point. Because of this, extreme scores will pull the mean towards them. This can be a serious issue at times. The second mathematical quality of the mean that I want to note is that the sum of the squared deviations about the mean is a minimum. What I mean, no pun intended, by this is that if you subtract the mean from each score, square the result, and then add up all of those values, the result will be smaller than any other number you could have selected for that subtraction. Let's see this in an example. We'll start with these 5 values, 2, 4, 5, 9, and 10. They sum to 30, so my mean is 6. I then subtract the mean 6 from each of those scores. Mathematically, we can write that as x minus x bar. That gives us -4, -2, -1, 3, and 4. Notice that these do sum to 0 just like we just said. We then square these values to get 16, 4, 1, 9, and 16. Notice all the negatives have disappeared. We then add up these to get 46, which is called the sum of squares. We'll come back to the sum of squares later and use it a lot in statistics. Did I say a lot? I meant to say that we will use the sum of squares a lot. Now, to see that the mean gives us the smallest sum of squares, let's redo these calculations but plug in a number that's not the mean. Instead, let's subtract 5 from each score instead of the actual mean, which we know is 6. Now, x minus 5 is equal to -3, -1, 0, 4, and 5. If we square those values, we get 9, 1, 0, 16, and 25. Adding them up, we get 51, which is larger than the sum of squares value we got using the mean. Again, in fact, any other number we use will always give us a larger value than using the mean. That's what we mean by the sum of squared deviations from the mean is a minimum. Let's talk about one final very nice quality about the mean that shows up in situations where you have different groups with different means and you want to calculate an overall mean across all of those different groups. Now, you might think, well, that's easy. I'll just take the mean for each of those groups and calculate the mean of those means. But if you think about it a bit, you should see that that approach usually won't work, or at least it may not give you the answer that you think it does. What if one of those groups was really large and another group was tiny? If you just take the average of those two means, that little group carries just as much weight as the huge group. Unless the two groups are also the exact same size, the mean of the group means isn't the same as the overall mean you would get if you calculated everybody in together. What we need to do is weight the group means by how many people are in each group. We call this the grand mean or the weighted mean. In this type of situation, we represent the grand mean as x double bar. That's just a way of letting us know it's the grand mean across multiple groups. The grand mean is equal to the sample size for group 1 times the mean for group 1 plus the sample size for group 2 times the mean for group 2, all divided by the combined sample sizes of groups 1 and 2 together. Again, the grand mean is the mean across all the data in all the groups. It's as if we threw everyone into one big bucket and calculated the mean. We'll later see how useful this can be at times. But now, what's particularly relevant for this discussion on measures of central tendency is that you can't do this with the median or mode. The median and mode don't allow for this type of calculation. Let's end this video here, and in our next video start with a discussion of the second measure of central tendency, the median. All right? Take care.